Hey everybody, I want to talk to you about errors in hypothesis testing. And errors are probably not what you're thinking they are. So let's talk about what they are. An error is, so I'm thinking of like a mistake as you did something wrong, right? Like you took a bad sample, or no, I don't want to use that one as an example. You calculated something wrong, right? That's a mistake. An error is something unlucky happened. Almost always this means you got a weird sample. Like your sample was like you did good procedures for getting your sample, and you just got super unlucky and it was very weird, right? You did the things that you need to do to avoid bias and get a representative sample, and somehow it just still didn't happen. This is called sampling error. This is super common actually, because you are always dealing with a subset of your population. You never have a completely perfect sample. And sometimes if your sample is weird enough, it might cause you to make the wrong conclusion in your hypothesis, or in your hypothesis test, right? Where your conclusion is like which hypothesis you believe, right? And if you choose the wrong one, that's an error. Now, here's the thing. You're never going to know. You're not going to know if you chose the wrong one or not, unless some future event tells you, because you're always going to choose the appropriate one based on the math, which we'll get into when we talk about p-values. But still, what can happen is you just get a strange sample that misleads you, and the thing you end up choosing doesn't actually reflect reality. So let me show you what I mean. Oh, the two types of errors that I'm talking about, by the way, are called type 1 error and type 2 error by statisticians. There are better names, and I will get to them in a couple of boards here. Where is my mouse cursor? Oh, gosh darn it. I know you guys probably laugh whenever I lose my mouse cursor. There it is. Sorry, it's white on white, and I have old eyes apparently. Okay, so here are the way you can distinguish type 1 and type 2 errors. There we have two things that we have. Try this again. The thing we believe is possibly reflective of reality and possibly not. So if the null hypothesis is actually true, so in other words, in reality, the null hypothesis is true, and we believe the null hypothesis is true, that is to say we don't reject it, great, no problem, we made the right choice, excellent job us. On the other hand, if the null hypothesis is actually true and we do reject it, we believe that the alternative is true, that's a type 1 error, right? So this happens when you think that your data is significant, or what's called statistically significant, which I will get to in the p-value section again, and it's not actually. Then that's a type 1 error. It's also called, well, we'll see in just a second. And the other way around is type 2, right? If the alternative hypothesis is actually true, but we think the null is true, that's a type 2 error. And again, of course, if the alternative is true and we believe it's true, then great, we made the right choice. So a type 1 error is when you reject the null hypothesis incorrectly, and a type 2 error is where you fail to reject the null hypothesis incorrectly, right? You should have rejected it and you didn't. All right. I am well aware that this is borderline impossible to remember if you have no context. So let us get some context. So better names for type 1 and type 2 errors are false positive and false negative. Type 1 is a false positive, type 2 is a false negative. If you're already familiar with those things, then fantastic. That's just the way to remember. Type 1 false positive, type 2 false negative. If you're not, here's where here's a way you can remember. Like, I'm going to give you a scenario. So here's my example for the scenario. You go get a COVID test. You've probably done this. You are not exhibiting any symptoms, so there's no reason to think you actually do have COVID, but you go get a test for whatever reason. You want to come on campus, for instance. Now, when you take any medical test, it's actually a hypothesis test. They can be wrong. I think you guys probably know that medical tests can be wrong. They're not typically wrong, but there's a percentage chance. And so what they're doing is they're doing a hypothesis test with these as your hypotheses. The null hypothesis is that you don't have COVID, right? That's barring other information, you're not exhibiting any symptoms. There's no reason to believe you do have COVID. So our default belief is going to be that you don't have it. So unless we see evidence that you do have it, we will assume that you don't. Right? And the alternative, of course, is COVID. That's the one that requires proof, right? It requires not proof exactly, but evidence. You have to have evidence to think that you have COVID, usually presence of antibodies or however they do these tests. Right? And so testing positive means that you have COVID. That means that we've rejected the null hypothesis in favor of the alternative. That is a positive test. Right? And so the test thinks, I'm using a lot of air quotes today, sorry, the test thinks you have COVID if you test positive. Sometimes that's right, and sometimes it's not, right? So if we reject the null hypothesis, it means we think that you have COVID-19. This is not necessarily true. And if the test comes back positive, but you don't actually have the disease, that is a false positive. It's also a type 1 error, right? Because remember, type 1 error is when we reject the null hypothesis and believe the alternative when the null is actually true. Well, the null being true in this case means that you don't have it, and rejecting it means that we think you do have it. So if the test comes back positive, we think you have COVID-19, and then if you don't actually have it, that is a type 1 error or a false positive. The other way around is a false negative, right? If the test comes back negative, says you don't have COVID, but you actually do, that's a false negative and it's type 2 error. So that's where the terms come from, false negative and false positive. I believe they're from medical terminology. I actually don't know the etymology of those terms, but it makes perfect sense. Here's another way to keep them straight, and this is more relevant for us, which is researchers very often have a vested interest in rejecting the null hypothesis. If you are doing research and you have a hypothesis, you have a theory, and you test it, then that hypothesis that you make is going to be the alternative hypothesis in whatever hypothesis test you end up doing. If you don't reject your null hypothesis, you probably can't publish your paper, because papers rely on something interesting to be published, right? It makes sense from a conceptual standpoint that the journals publishing papers want to publish things that are interesting and new and fresh and not what everybody already thinks, right? Things that require proof, and here's the proof. That's the journal. The problem with this is that if you don't reject the null hypothesis, then you can't get your paper published, but that's actually still relevant information, right? If you don't, you have this theory and you test it and you gather all your data and you're very careful and you do a great job testing it and the results come back and you don't reject your null hypothesis, that means that the evidence that you gathered and all the science that you did does not support this hypothesis that you have. That's actually very valuable information. It's boring information, but it's very valuable, because then somebody else who's got the same theory might not be inclined to go test it. And it would be nice if they had your data too. But you can't get a journal to publish it, because journals are independent money-making ventures. So they want to publish in interesting things on important topics. And if the thing that you have either isn't interesting or isn't important or both, you can't publish it. So researchers often will be pretty aggressive with their data, pretty aggressive about finding ways to reject null hypotheses. This is not good science. It's not good research. You shouldn't do it. But the financial and career incentives are there to do it. And I will talk more about this when we talk about p-values. I know I'm putting everything in the p-value video, and there's a good reason. It's going to be a big one. But there are good reasons why you want to reject your null hypothesis for your career and your money situation. Consequently, I think of making a type 1 error as being too aggressive with your data, being too willing to believe your own hypothesis and reject the null hypothesis. And a type 2 error is being too cautious, not rejecting the null hypothesis even when there's enough evidence. Now, that's not exactly right, because it's the data that will tell you to reject or not reject the null hypothesis. You're not really making a choice so much as you are reporting what the data says. But that is a way to think of it, is like type 1 error is rejecting the null hypothesis even when it's true, right? You're being too gullible, essentially. And type 2 is not rejecting the null hypothesis even though it's false. That's being too conservative, right? You're not seeing the pattern that's actually there, kind of thing. So, I guess before I leave this page, I want to say the following thing. I don't know how plugged into academia you guys are, but there is a tremendous problem with too many type 1 errors in publications. It is only relatively recently, only maybe the last, 10 years, something like that, that this has really come to the forefront of academia. But it's a huge problem. So just a little preview, we usually accept a 5% probability of making a type 1 error. So you might think that, well, okay, if every study you do has a 5% probability of making a type 1 error, then presumably in the journal publications, 5% of those would have type 1 errors in them. That's not it at all. Various estimates range between 40 and 60% of journal articles having a type 1 error. That is a lot. I'm not going to go into it in this video, but there's a lot to look into there, actually, believe it or not. Yeah, I'm sorry, I'm about to go off on a tangent. I'm not going to. I just want to do my last page and be done. So here's the notation for errors. Probability of making a type 1 error is notated. This is an alpha. This is a Greek lowercase a. Just a drawing tip. If you want to make an alpha, draw a fish. Just don't finish the tail. There you go. There's an alpha. It's called the significance level. We will use this all the time in literally every hypothesis test. Every hypothesis test has a significance level, and we need to know alpha every time. In practice, as you'll see when we actually do some hypothesis tests, we choose it. We just say alpha is 5%, and you'll see why we do that in the p-value video. Probability of making a type 2 error is notated beta. It's a lowercase, or it looks like a capital B, but that's actually a lowercase beta. The way to make them is to start at the tail and then round up like this. There's a nice little beta. I don't know what else it looks like other than a B with a curvy top and a tail on the bottom. So I can't tell you to draw a fish. But yeah, you draw it like I just did there, right? Start at the bottom, go up and around. Beta doesn't have a special name because we don't care about beta. I know that sounds strange. You might think type 1 error, type 2 error, one's a false positive, one's a false negative. Both are bad in their own ways. How come one is so much more important than the other? I will tell you in the p-value video why one is so much more important than the other. Anyway, so what we end up doing is choosing alpha to be usually 5%. That's the standard. It can be anything we want, technically, anything greater than 0 and less than 100. We can't choose it to be 0, though. And again, I will explain, not in the p-value video this time probably, but in the last video for this topic, which I believe I have titled Why We Compare the P-Value to Alpha, which sounds like I can answer that in a sentence, and I cannot. That's going to be a long discussion. Anyway, alpha and beta are inversely related in general. If alpha goes up, beta goes down. If beta goes up, alpha goes down. We don't care about that relationship. I'm just sort of telling you for completeness, I guess. We're only going to use alpha. We will never calculate beta. we're not going to. It's actually very hard to calculate beta. It's well beyond the level of this course, and we don't care about it anyway. If you go further in statistics, you will end up dealing with beta, but no more in this class. Just know what it is. Yeah, so we're going to end up using alpha in every hypothesis test and beta absolutely never. And we're gonna ignore beta entirely. So I am just going to leave it at that. I've put off a lot of stuff to the p-value video. I should probably shoot the p-value video. And so I'm going to go ahead and leave it there. I know there's not a lot of examples here, but there's not a lot to tell you, or there's not a lot to do with errors. What we'll do in the homework is I'll ask you to interpret like which kind of error could happen in this case. And when I actually do a hypothesis test in p-value video, I will show you what I mean by that. But for now, I'm going to go ahead and stop there, and I will catch you guys in the next video.